Imagine standing on a vast, dark plain beneath a canopy of stars that stretches out to the very edges of existence. The world around you is completely silent, wrapped in the cool embrace of the midnight air. As you look up, you notice the moon, a brilliant silver crescent hanging suspended in the velvet sky. It moves with a slow, majestic certainty, tracing the exact same path it has traveled for billions of years. Now, look down at your feet. Reach out your hand in your mind and pick up a small, smooth pebble from the earth. Hold it for a moment, feeling its cool weight against your skin, and then simply let it go. It drops instantly, falling in a straight, unwavering line until it strikes the ground with a dull thud, coming to an immediate and absolute rest. For thousands of years, this simple contrast was the greatest mystery in the human experience. To the ancient philosophers, the universe was fundamentally fractured into two completely different worlds that operated on entirely different sets of spiritual and physical laws. There was the earthly realm, the world beneath the moon, where everything was imperfect, temporary, and heavy. In this lower realm, the natural state of matter was thought to be absolute stillness. If you wanted to move a cart, you had to pull it. If you stopped pulling, the cart came to a stop. If you threw a spear, it eventually lost its unnatural life and tumbled to the dust. Movement was seen as an effort against the natural order, a temporary disruption of a cosmic desire for rest. But when those same observers looked above the clouds, they saw the celestial realm, the world of the stars, the sun, and the planets. This upper world appeared to be made of an entirely different substance, a perfect, weightless ether. Up there, things did not fall, they did not decay, and they never, ever came to a rest. Instead, the planets moved in eternal, flawless circles, driven by an inherent, divine perfection that required no pushing or pulling to maintain. For generation after generation, humanity accepted this deep division, believing that the rules governing a falling stone on Earth had absolutely nothing to do with the rules governing the grand architecture of the heavens. But as the centuries turned, a quiet revolution began to take shape in the human mind, born from an insatiable desire to find a singular, unifying truth beneath the apparent chaos of nature. Thinkers began to ask a radical, almost dangerous question. What if the universe is not divided at all? What if the exact same invisible thread that pulls a stray autumn leaf to the damp earth is the very same thread that ties the moon to its eternal orbit around our planet? What if there is only one set of laws, written in a grand, universal language, that applies equally to the smallest grain of sand and the most massive star in the deep dark of space? This profound shift in thought marked the birth of classical mechanics, a journey of intellectual awakening that reached its absolute pinnacle in the work of Sir Isaac Newton. We are embarking together on a deep exploration of this beautiful, unified framework. As we walk through this landscape, you do not need to struggle to memorize formulas, nor do you need to strain your mind to grasp abstract mathematical symbols. Instead, let your breath slow down, allow your shoulders to drop, and simply let these foundational ideas wash over you like a calm, steady wave. We are going to strip away the dense, dry notation of the textbook and look directly at the elegant, living machinery of reality itself. To understand how this grand clockwork functions, we must learn to see the world not as a collection of isolated objects, but as a continuous web of relationships. Every movement you make, every breath you take, and every celestial body drifting through the void is participating in a grand, harmonious dance governed by three simple laws of motion and one universal law of gravity. These rules are so foundational that once you understand them conceptually, the entire physical universe transforms from a confusing jumble of random events into a beautifully predictable, deeply comforting masterpiece of order. Before Newton could map the paths of the planets, however, he had to completely redefine what it means for something to be at rest or in motion. He had to challenge the common sense wisdom of the ancient world and realize that our everyday experiences are often an illusion caused by hidden forces. When you see a rolling ball slow down and stop, your eyes are telling you that the ball naturally wants to rest. But this is a deception. The ball does not want to stop. It is being forced to stop by the invisible friction of the grass and the resistance of the air. If you could strip those hidden forces away, the true nature of matter would reveal itself. Imagine an environment completely empty of these hidden distractions, a realm of pure, undisturbed space, far away from the pull of any planet or the friction of any atmosphere. In this quiet void, the true behavior of matter becomes perfectly clear. An object left entirely to itself does not seek a state of rest. Rather, it seeks a state of consistency. It desires, with a deep and inherent stubbornness, to simply keep doing exactly what it is already doing. If it is sitting in the dark stillness, it will rest there, undisturbed, through the passage of eternity. If it is drifting through the void at a steady pace, it will continue to glide along that exact same straight path at that exact same speed forever, requiring no engine, no push, and no effort whatsoever to sustain its journey. This is the great threshold of classical physics, the realization that motion is just as natural as rest, and that change, not movement, is what requires an explanation from the universe. As we let our minds settle into this vast, orderly cosmos, we begin to see that the universe operates not on caprice or whim, but on a beautiful, unbroken ledger of cause and effect. Every action is accounted for. Every change in speed has a specific source, and every object in existence is bound by the exact same mathematical harmony. And with that understanding quietly in place, we are naturally led to ask, what exactly happens when an object is left completely to itself, untouched by the outside world? That is what we will gently explore next. The principle of inertia and the first law of motion. A moment ago, we ended with the profound realization that motion is just as natural as rest, and that change itself is what demands an explanation from the universe. Let us pick up that thread right where we left it, stepping across the threshold of the ancient world and into the brilliant, clear light of what we now call Newton's first law of motion, or the grand principle of inertia. To truly appreciate this concept, we must train our minds to look past the messy, friction-filled world we live in every day, and instead visualize a landscape of absolute physical purity. Picture in your mind a vast, infinite frozen lake under a quiet, starlit sky. The ice stretching out before you is not ordinary ice. It is perfectly smooth, utterly devoid of any bumps, ridges, or microscopic roughness. It is a surface of absolute idealized perfection, completely free from the grasping hands of friction. Furthermore, imagine that the air above this lake is entirely gone, leaving a warm, gentle vacuum where not even a single molecule of gas exists to brush against a moving object. Now, imagine you are holding a single, heavy stone made of smooth, polished marble. You kneel down on this perfect ice, take a deep, slow breath, and give the stone a gentle, steady push, releasing it so that it glides away from you into the darkness. In our everyday world, if you slide a stone across a real frozen pond, your common sense tells you exactly what will happen. The stone will journey for a short distance, gradually slowing down, losing its energy, and eventually coming to a dead stop. For thousands of years, brilliant thinkers looked at that exact phenomenon and concluded that the stone stopped because its internal impetus ran out, or because stillness was the natural state it desperately wanted to return to. But in our idealized world of perfect ice and empty air, a miracle of pure physics unfolds. Because there is no rough ice to grind against the bottom of the stone, and no air resistance to push against its front, there is absolutely nothing in existence to steal its motion away. As you watch the stone glide away from your hand, it does not slow down by even a fraction of a mile per hour. It does not swerve to the left, nor does it drift to the right. It travels at an absolutely constant, unvarying speed, tracing a line that is as perfectly straight as a laser beam. Minutes pass, then hours, and then days. The stone simply continues its journey, effortlessly coasting across the infinite expanse, maintaining its velocity through the sheer, quiet dignity of its own existence. It requires no engine to keep it going, no continuous push from behind, and no renewal of energy. The motion itself is a state of being, a continuous property that belongs to the stone just as much as its color or its shape. It will glide onward in a straight line forever, until the very end of time, unless it encounters an outside obstacle. This is the living essence of the first law of motion, traditionally stated as, an object at rest will remain at rest, and an object in uniform motion will remain in that exact state of uniform motion along a straight line, unless it is compelled to change its state by forces impressed upon it. It is a law of profound cosmic laziness, a declaration that matter is fundamentally conservative. Matter has no internal desire to change its behavior. If an object is sitting quietly in the dark stillness of space, it will rest there for eternity, cradled in its own immobility, completely incapable of moving a single inch on its own. Conversely, if an object is already moving through the void, it will keep moving with the exact same speed and in the exact same direction forever, completely incapable of slowing down, speeding up, or turning on its own accord. To fully grasp this at a deeper, college-ready level, we must understand that inertia is not an active force. It is not an energetic shield or a ghostly pressure pushing back against the world. Rather, inertia is an inherent, passive property of all physical matter. It is the measure of an object's fundamental stubbornness, its total, unyielding resistance to any change in its current state of motion. When an object has a large amount of inertia, it takes a massive amount of external influence to alter what it is doing. Think of a time when you have been a passenger in a car, sitting back comfortably as the vehicle cruises down a long, straight highway at 60 miles per hour. Because you are traveling inside the car, your body is also moving forward at 60 miles per hour. Your eyes might tell you that you are perfectly still, but your physical mass carries an immense amount of forward momentum. Suddenly, ahead of you, a traffic light changes to red and the driver presses down firmly on the brakes. The car grinds to a sudden halt, but what does your body do? Instantly, you feel yourself thrown forward, your chest pressing firmly against the fabric of your seatbelt. What is happening in that brief, breathless moment? It is not that a mysterious, invisible ghost has reached out from the dashboard and yanked you forward. No, it is simply your own inertia at work. When the brakes are applied, the friction of the road stops the tires, and the tires stop the chassis of the car, and the seat presses against the driver. But the car cannot directly break your internal organs or your physical frame. Your body, obedient to Newton's first law, desires with all its might to keep doing exactly what it was doing a millisecond ago, traveling forward in a straight line at 60 miles per hour. Your body tries to fly straight through the windshield, continuing its original journey, and it is only the external, restraining force of the seatbelt pressing against your torso that breaks your inertia, forcing your body to match the new, stationary state of the car. The exact same phenomenon happens in reverse when the car is stopped at a red light, and the driver suddenly hits the gas pedal, accelerating forward with a roar of the engine. In that instant, you feel your head and shoulders pressed deeply back into the cushioned fabric of your seat. Once again, there is no invisible force pushing your chest from the front. Instead, your body was at rest, and it deeply desires to stay at rest. As the car leaps forward, it literally leaves you behind for a fraction of an inch, and your seat must physically push against your back, forcing your stubborn mass to overcome its rest and accelerate along with the vehicle. We see this elegant law playing out across every corner of our daily lives, hidden in plain sight. Think of a heavy bottle of ketchup that is nearly empty. To get the sauce to flow, you tip the bottle upside down and shake it downward vigorously, then suddenly stop the bottle in midair. The ketchup inside, which was moving downward rapidly along with your hand, possesses inertia. When your hand stops the plastic bottle, the liquid inside refuses to stop. Its inertia carries it forward, slamming it down into the neck of the bottle, where it can easily flow onto your plate. Think of a wet dog shaking its fur after a swim. As the dog twists its body rapidly back and forth, the water droplets on its coat are accelerated sideways. When the dog's skin reaches the end of its twist and snaps backward in the opposite direction, the water droplets, carrying forward inertia, refuse to turn around. They break free from the fur and fly outward in straight lines, leaving the dog dry and comfortable. Let us set these vivid images down now, letting them dissolve into the quiet background of our minds. We have established that matter is fundamentally stubborn, that it possesses a deep, unyielding desire to preserve its current state of rest or constant motion, and that it requires an external, disrupting influence to break this peaceful spell. So, what does this actually mean for how we measure this stubbornness? What gives one object more of this protective inertia than another? And how do we quantify the deep substance of matter itself? That is what we will gently explore next. The concept of mass as quantified inertia. Before we explore how motion changes, let us set that idea down for a brief moment and let our attention drift away from the paths of motion, focusing entirely toward the objects themselves. We have established that all matter possesses a fundamental, built-in stubbornness called inertia, a deep, unyielding desire to preserve its current state, whether that state is absolute rest or a steady, straight-line glide through the dark void of space. But as we look around our physical world, it becomes immediately obvious that this stubbornness is not distributed evenly. Some things are remarkably easy to influence, while other things possess a resistance so grand and formidable that they seem almost entirely immovable. What is the secret property hidden inside matter that dictates this difference? To explore this, let us return to our quiet, imaginary warehouse. The space is vast, cool, and perfectly still, filled with a soft, diffused light that drives away all shadows. In the center of this empty floor sit two large, identical wooden crates. From the outside, they look absolutely indistinguishable. They are made of the exact same pale pine wood, held together by the same iron nails, and they occupy the exact same amount of physical space. If you were to look at them with your eyes closed, relying only on a visual description, you would say they are twins. But let us step closer and interact with them physically to discover their true inner nature. You walk up to the first crate, take a deep, calm breath, and extend a single finger. You place the tip of your finger against the rough wood and give it a gentle, tentative push. Instantly, with a soft scraping sound, the crate slides smoothly across the concrete floor, gliding a few feet away with almost no effort at all. This crate is completely empty. It is light, cooperative, and offers very little resistance to your touch. Its inertia is small, meaning its state of rest is fragile and easily broken by a mere gesture from a single human finger. Now, you step over to the second crate. You place your finger against its side in the exact same manner, and you apply the exact same gentle push. This time, nothing happens. The crate does not budge. It does not even tremor. It feels as though it has been welded to the earth itself. You step back, place both of your hands firmly against the wood, plant your feet securely on the ground, and lean your entire body weight into it, straining your muscles. With a heavy, groaning protest, the crate finally slides an inch or two across the floor. What is the difference between these two identical-looking boxes? If we were to pry open the lid of the second crate, we would find the answer packed tightly inside. It is filled to the absolute brim with heavy, dense, solid blocks of refined iron. This difference in internal resistance is what we call mass. In the grand language of Newtonian mechanics, mass is not simply a descriptive word for how big something is, nor is it merely a synonym for how much an object weighs. Mass has a far more profound, foundational definition. It is the precise, quantitative measure of an object's inertia. Mass is the numerical value we assign to an object's fundamental stubbornness when we try to alter its motion. When you push the empty crate, you are dealing with a small amount of mass, which means you are encountering a very small amount of inertia. When you push the iron-filled crate, you are fighting against an immense quantity of mass, which means you are colliding head-on with a staggering, deep-seated desire to remain perfectly still. The iron atoms packed tightly inside that box are collectively shouting their refusal to change their behavior, and you must exert a massive amount of external physical effort to conquer that internal resistance. To elevate our understanding to a true college-level rigor, we must make a vital, critical distinction that often confuses the casual observer of the physical world. Mass is completely distinct from weight. In our everyday speech, we use these two words as if they mean the exact same thing. We step onto a scale in the morning to check our weight, and we measure it in pounds or kilograms, thinking we are measuring the amount of substance in our bodies. But in the pure, unclouded realm of physics, mass and weight are entirely different concepts, separated by a profound cosmic truth. Weight is a force. Specifically, weight is the measure of the gravitational pull exerted on an object by a massive body, like the earth beneath our feet. Weight is an external relationship. It is a measure of how hard the earth is pulling you down toward its core. Because weight depends entirely on gravity, it is a fickle, changing variable that alters depending on where you happen to be standing in the universe. To feel this truth, let us take our iron-filled crate on an imaginary journey through the cosmos. Suppose we place this heavy crate on a precision scale right here on the surface of the Earth. The scale registers a heavy weight, perhaps 600 pounds, because the immense mass of the Earth is pulling downward on the immense mass of the iron blocks with great intensity. Now, let us load this crate onto a starship, lift off from the Earth, and journey out into the deep, dark, empty void between the stars. We travel so far away from any planet, moon, or sun that gravity fades away to absolutely nothing. If you float inside the cabin of the starship and place the iron crate onto that same scale, the needle points to absolute zero. The crate is now completely, beautifully weightless. If you release it in midair, it does not fall to the floor. It hovers there peacefully in the quiet cabin, drifting like a cloud. It has no weight whatsoever, because there is no nearby planet to pull it downward. But now, ask yourself an essential question. Has the mass of the crate changed? Has the internal stubbornness of that iron vanished just because it is floating in the dark? Absolutely not. Inside the crate, the exact same number of iron atoms are still packed together just as tightly as they were back in the warehouse on Earth. The physical substance of the object is entirely unaltered. To prove this, imagine you float up to the hovering, weightless crate in space. You assume that because it weighs nothing, it must be harmless. You pull back your fist and strike the side of the crate with all your might, expecting it to toss away easily like a balloon. Instantly, a sharp pain shoots up your arm. Your hand breaks against the wood, and the crate barely moves, drifting away at a mere crawl. Why? Because even though the crate has zero weight, it still possesses 100% of its mass. It still has the exact same amount of inertia. It still possesses a massive, stubborn resistance to being accelerated from a state of rest. It takes the exact same amount of physical force to push that crate across the weightless cabin of a starship as it did to push it across the warehouse floor on Earth. Mass is an intrinsic property of matter. It is a permanent, unchanging signature that an object carries with it wherever it travels in the universe, completely independent of gravity. If we were to travel even further, landing our starship on the surface of the moon, we would find a middle ground. The moon is a smaller world than the Earth, possessing much less total mass of its own, which means its gravitational pull is only about 1/6 as strong as the Earth's. If you place our iron crate on the lunar dust, it weighs only 100 pounds instead of 600. A single human could easily lift it off the ground, marveling at how light it feels. Yet, if you were to try and run forward while carrying it, or try to swing it rapidly from side to side, you would find it just as difficult and clumsy to maneuver as it was on Earth. Its mass remains untouched, holding fast to its eternal, quantitative measurement of inertia. Let us plant this seed of understanding firmly and deeply in our minds as we prepare to take our next step. We now understand matter not just as a visual shape, but as a quantified collection of resistance. We see the world as a collection of masses, each holding its own protective shield of inertia, each requiring a precise amount of intervention to break its peaceful rhythm. Let us set this idea down now, fully formed, and let our attention drift away from the static, unchanging property of mass, and look toward what happens when a mass meets an active, external influence that breaks its balance. That is what we will gently explore next. Newtonian mechanics, dynamics, net force, and acceleration. A moment ago, we established that mass represents an object's deepest, internal resistance to change, an unchanging signature of substance that remains constant, whether an object is resting on the earth or floating weightlessly in the deep void of space. Now, let us introduce the concept that causes this stubbornness to yield, the active spark that breaks the peaceful spell of inertia and forces matter to rewrite its behavior. This is the concept of force, and the resulting phenomenon we call acceleration. Together, they form the core of dynamics, the branch of mechanics that explains not just how things move, but why they move the way they do. To truly understand how forces interact with mass, we must dispel the common misconception that a force is something an object possesses internally. An object cannot contain a force. A rocket does not store a force inside its hull, nor does a muscular athlete hold a force within their arms. Instead, a force is a purely relational event. It is an interaction between two entities, a push or a pull exerted by one object upon another. To visualize how these interactions shape reality, let us imagine a wide, beautifully calm lake at dawn. The water is as smooth as a sheet of glass, reflecting the soft, pale pinks and blues of the morning sky. In the exact center of this lake floats a small, wooden rowboat. It is completely still, casting a perfect, undisturbed reflection on the glassy water. Now, let us imagine that a gentle current begins to stir beneath the surface, pushing the boat directly toward the north with a subtle, steady pressure. If this were the only interaction, the boat would immediately break its rest and begin to drift northward. But at that exact same instant, a gentle morning wind begins to blow across the lake, pushing the hull of the boat directly toward the south with the exact same amount of steady pressure. Picture this scene in your mind. The underwater current is tugging the boat north, while the wind is pressing the boat south with identical strength. What happens to the wooden rowboat? It remains absolutely, perfectly still. Even though two distinct forces are actively acting upon the boat, its state of rest is completely undisturbed. Why? Because in the realm of Newtonian mechanics, when we talk about causing a change in motion, we can never look at just one force in isolation. We must always look for what physicists call the net force. The net force is the total, combined effect of all the pushes and pulls acting on an object after they have all fought it out, combined, and canceled each other out. It is the vector sum of all forces, a concept we can understand simply as the final, mathematical survivor of a cosmic tug-of-war. In the case of our rowboat, the northward force of the current and the southward force of the wind are equal in magnitude, but completely opposite in direction. They neutralize each other perfectly, leaving the net force at exactly zero. When the net force on an object is zero, the universe treats that object exactly as if no forces were acting on it at all. The protective shield of inertia remains unbroken. But now, imagine that the morning wind dies down, vanishing into a quiet whisper, while the underwater current continues to push toward the north with its original strength. Suddenly, the perfect balance is shattered. The tug-of-war is over, and there is now a net force greater than zero pointing directly toward the north. In that exact millisecond, the rowboat's inertia is conquered. The boat breaks its stillness and begins to move. This brings us to the profound definition of acceleration. In everyday speech, we use the word acceleration to mean that something is speeding up, like a sports car racing away from a green light. But in the precise, college-level language of physics, Acceleration has a much broader, more elegant definition. It is the rate at which an object's velocity changes over time. And because velocity includes both speed and direction, acceleration occurs whenever an object speeds up, slows down, or changes its direction of travel. Acceleration is the physical manifestation of a net force at work. It is the visible evidence that matter's inertia has been overcome by an external influence. To feel the depth of this concept, let us visualize a car driving along a perfectly circular racetrack at night. The driver locks the cruise control at a steady, unchanging speed of exactly 30 miles per hour. As you watch the car from above, its headlights trace a beautiful, continuous circle in the darkness. If you were to look only at the car's speedometer, you might think that because the speed is constant, there is no acceleration taking place. But your physical intuition tells you otherwise. To keep the car turning along that curved track, the driver must keep their hands firmly on the steering wheel, continuously turning the front tires. The tires must continuously grip the asphalt, pushing sideways against the road. Even though the car's speed never changes by a single mile per hour, the car is undergoing continuous, constant acceleration. Why? Because its direction of travel is changing at every single fraction of a second. At one moment it is heading north, a moment later it is heading northwest, then west, then southwest. Because its velocity vector is constantly swinging inward toward the center of the loop, a continuous net force must be applied to make that happen. If the car were to hit a patch of slick oil on the track, destroying the tire's ability to push against the road, the net force would instantly drop to zero. In that exact moment, the acceleration would vanish, and the car would instantly fly off the track in a perfectly straight line, obedient once more to its natural inertia. Similarly, we must realize that slowing down is also a form of acceleration, often called negative acceleration or deceleration. Imagine a massive passenger jet touching down on a runway. The moment its wheels kiss the tarmac, the pilot deploys the thrust reversers and slams on the wheel brakes. A massive net force is applied in the direction completely opposite to the plane's forward motion. The speed of the aircraft drops rapidly, changing from 150 miles per hour to a gentle taxiing speed in a matter of seconds. Because the velocity is changing over time, this dramatic slowing down is just as much an acceleration as the initial takeoff roll. Every single shift in the rhythm of the physical world, the sudden stop of a baseball caught in a glove, the gentle curving of a thrown stone as it arches through the air, the violent shattering of a breaking wave, requires a net force to break the peaceful spell of inertia. Without a net force, the universe would be a static, unvarying landscape of straight lines and absolute stillness. Forces are the authors of change, and acceleration is the story they write upon the canvas of mass. Let us set these ideas down now, fully formed, allowing them to weave together in the quiet theater of your mind. We have seen how forces combine to create a net influence, and we have seen how acceleration measures the resulting transformation in an object's speed and direction. We are standing on the precipice of a grand synthesis, ready to look at how these separate threads of force, mass, and acceleration lock together into a single, beautiful mathematical relationship that governs the entire physical universe. And with that understanding quietly in place, we are naturally led to ask, exactly how much acceleration do we get from a specific amount of force, and how does the mass of the object dictate the final outcome of this interaction? That is what we will gently explore next. The quantitative relationship of force and motion. We have looked at mass as the quiet, intrinsic stubbornness of matter, and we have explored how net forces break that stillness to create acceleration, the changing of an object's speed or direction over time. Now, let us join these separate threads together into the crowning jewel of classical dynamics, Newton's second law of motion. This law does not merely state that forces cause acceleration. It provides the exact, rigorous, mathematical architecture that governs that relationship. Instead of relying on symbols or equations scratched onto a blackboard, let us listen to this cosmic relationship expressed in plain, elegant, and deeply intuitive English. The second law states that the acceleration of an object is directly proportional to the net force acting upon it, points in the exact same direction as that net force, and is inversely proportional to the mass of the object. To truly feel the profound truth of this statement, let us deconstruct it piece by piece, allowing our minds to visualize how these three variables balance each other out in the real world. Let us begin with the first part of the relationship, the direct proportion between force and acceleration. To imagine this, picture yourself on a warm, quiet, summer afternoon at a neighborhood park. You are standing behind a playground swing set. The swing is hanging perfectly still from its chains, and sitting in the seat is a small child, relaxing peacefully. Suppose you reach out your hands and give the back of the swing a very gentle, tentative push. Because you applied a small amount of net force, the swing responds by accelerating just a little bit, moving away from your hands at a gentle, slow pace. Now, let us imagine that on the next pass, you decide to push with a great deal more energy. You plant your feet, bend your knees, and push the back of the swing with twice as much physical strength as you did before. Because the swing's mass has not changed, the result is immediate and mathematically precise. The swing accelerates at exactly twice the rate of the first push, soaring high up into the air toward the sky. This is what it means for two properties to be directly proportional. If you double the force, you double the acceleration. If you triple the force, you triple the acceleration. If you reduce your force to a tiny fraction of its original strength, the acceleration drops by that exact same fraction. Force and acceleration are locked in a perfectly symmetrical dance, where the one always mirrors the actions of the other. But now, let us look at the second, more subtle half of the relationship, the inverse proportion between mass and acceleration. To visualize this, let us stay at our quiet park, but let us change the scenario slightly. Imagine that the small child steps off the swing and walks away to play in the sandbox. In their place, a fully grown adult, perhaps a defensive lineman for a football team, possessing a massive, heavy, and muscular physical frame, steps up and sits down on the tiny canvas seat of the swing. The chains groan slightly under the sudden increase in mass. You walk up behind this new passenger, plant your feet in the exact same position as before, and resolve to push with the exact same amount of maximum strength that you used on the small child's second push. You lean forward and strike the adult's back with all your might. What happens to the swing? It barely moves. It sluggishly breaks its rest, accelerating forward at a mere crawl, traveling only a few inches into the air before swinging lazily back toward you. What has gone wrong? Your force was exactly the same, but the resulting acceleration plummeted to a fraction of its previous glory. This is the law of inverse proportion at work. Because the adult possesses vastly more mass than the child, they possess vastly more quantified inertia, vastly more fundamental stubbornness, resisting any change in their motion. When mass increases, the resulting acceleration must decrease for the same given force. If you double the mass of the object you are trying to move, you will find that your force yields exactly half the acceleration it did before. If you multiply the object's mass by 10, your acceleration will be cut down to a mere tenth of its original value. Mass acts as a grand dampener on the ambitions of force, a cosmic brake that prevents objects from changing their velocity too quickly. When we synthesize these two beautiful opposing principles into a single conceptual statement, we find that net force is equal to the mass of an object multiplied by its acceleration. This simple verbal equation is the emotional and intellectual core of classical mechanics. It bridges the gap between the invisible world of intent, the pushes and pulls we exert, and the visible world of geometry, the distances and speeds we can measure with a stopwatch and a ruler. It tells us that if you want to know how much an object will accelerate, you must take the total net force pushing it forward and divide it by the object's total mass. To appreciate the college-level rigor of this law, we must realize that it allows us to predict and calculate the behavior of absolutely everything in our physical universe, spanning an incredible range of scales. Imagine a massive diesel locomotive sitting at the front of a freight train that stretches for 2 miles across a flat Midwestern plain. The train is completely stationary, holding thousands of tons of steel, coal, and cargo. When the engineer pulls the throttle lever forward, the colossal engines roar to life, generating millions of units of force that press the steel wheels against the tracks. Because the mass of the train is so unimaginably vast, the initial acceleration is almost imperceptible. The train does not leap forward like a sports car. Instead, it inches forward, gaining only a fraction of a mile per hour every few seconds. It takes miles of constant, unyielding force for that small acceleration to finally accumulate into a roaring, high-speed cruise. The second law explains this slow build perfectly. A huge force divided by an astronomical mass yields a tiny, patient acceleration. Now, contrast that massive train with the tiny, delicate mechanism inside a modern smartphone. Inside the phone's camera module sits a microscopic stabilizer, a tiny piece of silicon that moves a lens back and forth to keep your photos from blurring when your hand trembles. The mass of this tiny lens is less than a single grain of salt. Because the mass is so vanishingly small, even the tiniest microscopic pulse of electrical force from the phone's battery causes the lens to accelerate at a staggering rate, darting back and forth thousands of times in a single second to correct for the motion of your fingers. A tiny force divided by a microscopic mass yields an explosive, blindingly fast acceleration. The second law also reveals a deep, comforting symmetry when objects find themselves falling through space. Think back to our earlier thought experiment where a heavy cannonball and a tiny marble dropped at the exact same rate in a vacuum. Newton's second law is the exact reason why this happens. The Earth pulls on the heavy cannonball with a massive amount of gravitational force because it has a huge mass. You might think that this huge force would make it fall faster. But because the cannonball has a huge mass, it also has a huge amount of inertia, meaning it requires that exact same huge force just to get it moving at a normal pace. The extra force is completely used up conquering the extra mass. The two properties perfectly cancel each other out, leaving the cannonball to accelerate at the exact same rate as the tiny marble, which requires only a tiny force to conquer its tiny inertia. Let us set these profound relationships down now, allowing them to find a comfortable, quiet home within your thoughts. We have seen how force, mass, and acceleration form an unbreakable logical trinity that dictates the movement of all things, from trains crossing continents to lenses shifting inside silicon chips. And with that understanding quietly in place, we are naturally led to ask, where do these forces come from? Do they ever exist entirely on their own as isolated sources of power, or is every push in our universe bound to another, hidden counterpart. That is what we will gently explore next. The interconnected universe, action and reaction pairs. So what does this actually mean for how objects interact with one another? Let us step deeper into the tapestry of classical mechanics and explore a truth that is both deeply profound and comforting in its symmetry. Up until this point, we have focused our attention on a single object reacting to an external net force. We watched a stone glide across the ice, a crate resist a human hand, and a playground swing accelerate into the air. But if we stand back and look at the entire cosmos with wide, unclouded eyes, we discover a beautiful, universal rule. In our physical reality, no force ever exists in absolute, lonely isolation. Forces are never independent entities that wander through space looking for a target. Instead, a force is always, without exception, a mutual interaction between two distinct entities. You cannot have a push without something being pushed. And more importantly, that which is pushed always pushes back. This brings us to the majestic threshold of Newton's third law of motion, a principle that dictates the perfect, unbreakable balance of the universe, often expressed in the timeless phrase, "For every action, there is an equal and opposite reaction." To truly understand this law, at a rigorous, college-ready level, we must carefully unpack what the words action and reaction actually mean. In everyday language, these words imply a sequence of events, a cause followed by an effect. You take an action, and then, a moment later, someone else reacts to what you did. But in the pure, instantaneous realm of Newtonian physics, action and reaction happen at the exact same cosmic microsecond. They are two sides of the very same coin. When object A exerts a force on object B simultaneously exerts an economic, perfectly identical force on object A, pointing in the exact opposite direction. The universe maintains a flawless, unbroken ledger of physical interactions. You cannot touch without being touched in return. To paint a clear picture of this symmetry in your mind, let us imagine a serene, timeless scene. Picture yourself standing on a completely frozen, perfectly smooth pond at twilight. The air is still, and the ice is so slick that your boots have absolutely no traction. You are wearing a pair of sharp ice skates, standing completely motionless in the center of the rink. A few feet in front of you stands a close friend, also wearing ice skates, completely stationary and facing you. Suppose you reach out your hands, place them flat against your friend's shoulders, and decide to give them a gentle, firm push to slide them away from you. What happens in that exact, breathless instant? Your conscious mind intended to move your friend. You applied a forward force to their shoulders, and obediently, your friend breaks their rest and begins to glide gracefully backward across the ice away from you. But look down at your own feet. In the exact same millisecond that your friend began to move away, you find your own body gliding backward in the completely opposite direction. Even though your friend remained entirely passive, never lifting a finger to push you, you were thrown backward, just as surely as they were. Why? Because according to the third law, your hands could not press against your friend's chest without your friend's chest pressing back against your hands with the exact same amount of force. The ice offered no friction to anchor you, revealing the hidden, reciprocal nature of the interaction. The force was a singular bridge built between your two bodies, pushing you both apart with perfect, geometric equality. Now, you might ask a brilliant, deceptive question that has puzzled physics students for centuries. If every single force in the universe is always accompanied by an equal and opposite force, why does anything ever move at all? Shouldn't these twin forces constantly fight each other to a draw, canceling each other out perfectly and leaving the world in a state of permanent, frozen paralysis? To solve this beautiful riddle, we must remember a crucial rule from our exploration of net forces. Forces can only cancel each other out if they are acting on the exact same object. Action and reaction pairs never act on the same object. They are always distributed between two different entities. To visualize this, let our minds drift to a rural countryside where a majestic horse is harnessed to a heavy wooden cart filled with hay. When the horse decides to move forward, it leans into its harness and pulls the cart. According to the third law, the cart pulls back on the horse with the exact same amount of force. If we look only at the connection between the horse and the cart, the forces are equal and opposite. So why does the cart move? Because we must look at the forces acting on each object independently. The horse is not just connected to the cart. The horse is also interacting with the earth. The horse plants its iron shoes firmly into the dirt and pushes backward against the ground. In response to this action, the massive ground pushes forward on the horse's shoes with an equal and opposite reaction force. It is this forward force from the ground that accelerates the horse. Meanwhile, the cart simply experiences the forward pull of the harness, which overcomes the friction of its wooden wheels. The system moves because the forces are acting on different bodies, weaving them together into a progressive stream of motion. Once you learn to see the world through the lens of the third law, you begin to notice action-reaction pairs, hiding in every breath, every step, and every triumph of human engineering. Think of what happens when you decide to take a gentle walk through a quiet garden path. To move forward, you do not simply lean your body into the air. Instead, you step forward, plant the sole of your shoe onto the gravel, and physically push the earth backward behind you. Because the earth is unimaginably massive, its inertia is too grand for your foot to move it in any noticeable way. But in response to your backward push, the earth instantly applies an equal and opposite forward force to the bottom of your shoe. It is literally the planet itself pushing you forward, acting as the launch pad for your every step. When you walk, you are dancing with the entire mass of the globe. Let us expand our vision now, lifting our thoughts away from the ground and looking up at a giant rocket ship clearing the launch pad at Cape Canaveral. The countdown reaches 0, and the colossal metal structure, weighing millions of pounds, begins to rise into the dark sky. The casual observer thinks that the rocket rises because the roaring exhaust gases are pushing down against the concrete launch pad, using the ground as a springboard to leap into the air. But this is an illusion. A rocket can launch just as easily in the absolute vacuum of deep space, where there is no launch pad and no atmosphere whatsoever. The true secret of rocketry is pure, unadulterated third law physics. Inside the rocket's combustion chambers, liquid fuel is ignited, creating a massive, high-pressure explosion. The engine architecture forces these hot, expanding exhaust gases to be expelled downward through the nozzle with a staggering, violent force. This downward torrent of gas is the action. Instantly, in accordance with the eternal laws of nature, the gas pushes back up on the top of the rocket engine with an equal, opposite, and terrifyingly powerful reaction force. It is this upward reaction from its own fuel that lifts the colossal metal structure toward the heavens. The rocket literally throws mass out of its bottom, so that the remaining mass can fly out of the top, pushing itself forward by throwing a part of itself away. Let us set these grand, explosive images down now, letting the roar of the rocket engines fade away into a quiet, gentle murmur. We have seen how the third law enforces a beautiful, unbroken harmony across the cosmos, ensuring that every push has a partner, every action has a mirror, and no object can ever affect another without being affected in return. We see the universe as an intricately balanced network of relationships, where all forces are held in a grand, symmetrical embrace. And with that understanding quietly in place, we are naturally led to ask, what happens when these shifting actions and reactions settle into a state of perfect, undisturbed harmony? How does the universe look when all these competing pushes and pulls balance the ledger completely, creating a state of absolute physical peace? That is what we will gently explore next. Classical equilibrium, static and dynamic balances. Let us pick up the thread of balanced forces and explore a state of profound physical peace known to mechanics as equilibrium. Up to this point in our journey, we have spent much of our time watching what happens when things change, when the quiet spell of inertia is broken, when net forces conquer mass, and when acceleration rewrites an object's speed or direction. But a massive portion of our physical universe is not in a state of wild, accelerating transformation. Instead, much of the world around us exists in a state of beautiful, poised stability, where all the competing pushes, pulls, actions, and reactions settle into a perfect mathematical tie. In the rigorous language of classical mechanics, an object is defined as being in a state of equilibrium when the net force acting upon it is absolutely zero. When this occurs, the universe experiences a moment of perfect mechanical balance, a peaceful harmony that manifests in two beautiful, distinct forms: static equilibrium and dynamic equilibrium. To truly understand the depth of this balance, let us first visualize the world of static equilibrium, the peace of absolute immobility. Imagine wandering deep into a quiet, ancient forest at twilight. The wind has died down entirely, leaving the leaves on the trees perfectly still. As you walk along a mossy path, you come across a clearing where a magnificent, ancient stone archway stands, built by human hands centuries ago. Step closer in your mind and look at how this archway is constructed. It consists of heavy, rough-hewn blocks of granite, wedged together in a graceful curve that rises over the path, held in place by a single, wedge-shaped stone at the very top, known as the keystone. Think about the immense forces acting upon this ancient structure. Every single block of granite is incredibly dense and heavy, filled with an enormous amount of mass. Because of this mass, the entire gravity of the Earth is continuously tugging downward on every single stone, pulling them toward the center of the planet with an unrelenting, silent force. If the stones were floating in the air, they would crash to the Earth in a violent fraction of a second. Yet, the archway stands, perfectly motionless, having survived the passing of hundreds of winters without shifting by a single millimeter. Why? Because it exists in a flawless state of static equilibrium. As gravity pulls the keystone downward, the wedge shape of the stone forces it to press outward against the stones, immediately to its left and right. Those stones, in turn, pass that crushing pressure down through the curved sides of the arch until the force reaches the vertical columns resting on the ground. Finally, the heavy base of the archway presses down onto the solid bedrock of the Earth with a massive action force. Simultaneously, obedient to Newton's third law, The bedrock presses back upward against the stones with a reaction force of identical strength. If you were to isolate any single block of stone in that archway and examine the ledger of its forces, you would find a perfect balance. The downward pull of gravity and the downward pressure from the stones above are perfectly neutralized by the upward push from the stones beneath it and the inward squeeze from the sides. The net force on every single atom of granite is exactly zero. There is no net force, therefore there is absolutely no acceleration. And because the structure started at rest, its velocity remains at zero. It is a monument to absolute stillness, a state where immense, terrifying structural forces are locked in a permanent, silent embrace, canceling each other out so perfectly that the result is an enduring, peaceful peace. Now, let us let our minds drift away from this motionless forest and journey toward a much more subtle, deceptive kind of mechanical balance, the state of dynamic equilibrium. It is a common misconception to believe that equilibrium only applies to things that are stopped dead in their tracks. But remember the pure definition of the first law of motion. An object will maintain its constant, straight-line velocity unless acted upon by a net force. If the net force on an object is zero, its acceleration is zero, which simply means its velocity cannot change. If that object happens to be moving when the forces balance out, it will simply continue moving at that exact same speed, along that exact same straight path, forever. This is dynamic equilibrium, the peace of perfectly steady, unvarying motion. To feel the truth of this concept, let us visualize a thrilling, breathless scene. Imagine looking up into a vast, open blue sky on a clear afternoon. High above the clouds, a skydiver has just leapt from the open door of an airplane. In the first few seconds of the jump, the skydiver's experience is one of wild, accelerating chaos. The massive gravity of the Earth pulls downward on their body with a heavy, constant force. Because they have just left the stationary plane, there is initially no air resistance to oppose them. With a net force pointing straight down toward the ground, the skydiver undergoes a rapid acceleration. Their downward speed, plummeting faster and faster with every passing heartbeat, gaining roughly 9.8 meters per second of speed every single second. But as the skydiver drops faster and faster through the sky, they begin to collide with the atmosphere. The air is not empty space. It is filled with billions of microscopic gas molecules. As the skydiver's body plows through these molecules at high speed, the air resistance pushes back upward against their chest and limbs, acting as a gaseous brake. At first, this upward air resistance is small, far weaker than the heavy downward pull of gravity, so the skydiver continues to speed up. But as their velocity grows, the air resistance rushes past them with increasing fury, growing stronger and stronger, packing a greater upward punch with every passing second. Eventually, a magical, mathematical moment of pure physics occurs. The skydiver reaches a speed so grand, perhaps 120 miles per hour, that the upward pushing force of the air resistance grows to become exactly equal to the downward pulling force of gravity. Picture this balance in your mind. Gravity is pulling the skydiver down with a force of, say, 180 pounds, while the rushing wind is lifting them up with an upward force of exactly 180 pounds. The two forces are perfectly matched in strength and completely opposite in direction. The tug of war has ended in a flawless tie. In that exact instant, the net force acting on the skydiver drops to absolutely zero. And because the net force is zero, Newton's second law dictates that the skydiver's acceleration must also instantly drop to zero. They completely stop speeding up. They do not freeze in midair, nor do they start floating upward like a balloon. Instead, they enter a state of dynamic equilibrium. They continue to fall toward the Earth, but they do so at an absolutely constant, unvarying, and steady speed, known as terminal velocity. They glide through the atmosphere at a predictable, smooth cruise, experiencing a strange, serene sensation of weightlessness and balance, despite traveling at blinding speed. The forces are in a perfect, dynamic tie, demonstrating that an object can be in total mechanical balance while participating in a high-speed journey. We see these two forms of equilibrium sculpting the stability of our entire world. Think of a massive cargo ship cruising across the Atlantic Ocean at a steady 15 knots. The forward thrust of its giant propellers is perfectly balanced by the backward drag of the ocean water, leaving the ship in dynamic equilibrium. Think of a heavy picture frame hanging straight on a living room wall. The downward pull of gravity is perfectly balanced by the upward tension of the wire, holding it in static equilibrium. Let us set these thoughts down now, letting the stone archway and the falling skydiver fade into the quiet background of your mind. We have seen how the universe balances its ledger, using a zero net force to create both absolute stillness and perfectly steady motion. We understand that equilibrium is not the absence of force, but the perfect, symmetrical locking of forces into a state of total harmony. And with that understanding quietly in place, we are naturally led to ask, what happens when we look at an object's total quantity of motion during these interactions? And how does the universe protect that motion when objects collide with one another? That is what we will gently explore next. Momentum and its conservation in isolated systems. As we continue our gentle journey through the mechanics of nature, we encounter a concept that combines the essence of mass and motion into a single flowing quality: momentum. Up until now, we have looked at mass as a static measure of an object's stubbornness and velocity as a measure of its speed and direction. But when these two physical properties marry, they give birth to a dynamic, sweeping value that dictates how objects interact when they cross paths and collide. Conceptualized simply, momentum is mass in motion. It is a measure of how difficult it is to bring a moving object to a complete and absolute stop. To truly feel the intuitive truth of this concept, let us listen to its mathematical relationship expressed in plain, elegant English. Momentum is equal to the mass of an object multiplied by its velocity. Because it is a simple multiplication of these two traits, an object can possess an immense, terrifying amount of momentum in one of two ways. It can either possess an ordinary amount of mass moving at an absolutely blinding, astronomical speed, or it can possess an extraordinary, colossal amount of mass moving at a slow, patient crawl. Let us paint a clear picture of this difference in your mind to feel its symmetry. Imagine standing at the edge of a beautiful, quiet harbor at twilight. The water is completely still, reflecting the deep indigo hues of the evening sky. Two entirely different vessels are moving toward the wooden dock, and by a strange coincidence, they are traveling at the exact same slow, gentle speed of just 2 miles per hour, a pace no faster than a leisurely stroll. The first vessel is a small, lightweight kayak made of molded fiberglass, steered by a single paddler. Because the combined mass of the kayak and the person inside is very small, its total momentum is remarkably low. If the kayak were drifting directly toward the wooden dock where you stand, you could easily lean forward reach out a single hand, press your palm against the bow of the boat, and bring it to a gentle, smooth stop without breaking a sweat. Your hand easily applies the small force needed to drain away its tiny quantity of motion. The second vessel, drifting toward that same dock at that same slow crawl of 2 miles per hour, is a colossal, ocean-going container liner. It stretches for thousands of feet across the water, laden with mountains of heavy steel shipping containers. Its mass is measured in hundreds of thousands of tons. Because its mass is so staggeringly vast, its total momentum is absolutely immense, even though its speed is nothing more than a lazy drift. If this giant ship were to glide toward the wooden dock, and you were foolish enough to reach out your hand to stop it, you would feel as though you were trying to halt a moving mountain. The ship would plow right through your hand, crush the wooden dock into splinters, and slide far up onto the shore before finally coming to a rest. The sheer quantity of its motion is unstoppable because its astronomical mass multiplies its tiny speed into a formidable physical value. Conversely, a tiny object, like a metal bullet weighing only a fraction of an ounce, can possess that exact same terrifying level of momentum simply by traveling through the air at thousands of miles per hour. A tiny mass, multiplied by an explosive velocity, yields a force that can pierce through solid steel. Now that we understand what momentum is for a single object, let us step up to a grander, college-level perspective and examine what happens when multiple moving masses interact with one another inside what physicists call an isolated system. An isolated system is a beautiful, idealized laboratory of the mind, a space completely cut off from the distractions of the outside world, where no random external forces like friction, air resistance, or gravity are allowed to interfere with the participants. Inside this quiet sanctuary of pure physics, a majestic, unbreakable law reveals itself, the law of conservation of momentum. This law states that the total momentum of an isolated system remains absolutely constant and unchanging over time, regardless of what violent changes, crashes, or explosions happen internally among the objects themselves. The universe keeps a flawless, unyielding ledger of motion. It never creates new momentum out of nothing, nor does it ever allow even a single fraction of momentum to vanish into the dark. It merely passes the quality from one hand to another, like a sacred, unending conversation. To watch this beautiful conservation unfold, let us visualize a classic, elegant scene. Picture a beautiful billiard table draped in smooth, vibrant green felt, sitting in a quiet, undisturbed room. For the sake of our experiment, let us imagine that this table is a perfect, isolated system, where the felt offers absolutely no friction to slow down the balls, and the air is completely still. Resting in the exact center of this table is a single, glossy white cue ball, sitting in a state of absolute, motionless peace. Its velocity is zero, which means its momentum is also exactly zero. A few feet away sits a second ball, identical in mass, but this ball is rolling smoothly across the green felt, traveling in a straight line directly toward the stationary white ball at a steady speed. This moving ball carries a specific, clear quantity of momentum. Now, close your eyes in your mind and listen to the event. With a soft, sharp click, the moving ball strikes the stationary ball head-on. In that exact microsecond of impact, a beautiful transfer of physical grace takes place. The ball that was originally rolling comes to an absolute, immediate dead stop. It surrenders its motion entirely, freezing in place on the green felt. But its momentum cannot simply disappear into nothingness. In accordance with the law of conservation, that exact, precise quantity of momentum is instantly poured into the second ball. The white cue ball, which had been resting in deep stillness, springs to life and rolls forward, traveling away from the point of collision along the exact same straight line, moving at the exact same steady speed that the first ball possessed before the crash. If you were to measure the total momentum of the system before the click and compare it to the total momentum after the click, you would find that the ledger balances to the absolute decimal point. The motion was not lost. It merely changed its address. This grand law governs every single interaction in our physical reality, from the subatomic collisions of particles inside a particle accelerator to the grand cosmic mergers of distant galaxies. Think of a giant cannon sitting on a wooden carriage, completely stationary on a battlefield. Because nothing is moving, the total momentum of the cannon and the heavy iron cannonball inside its barrel is exactly zero. Suddenly, the gunpowder ignites, and the cannon fires. The heavy iron ball is blasted out of the front of the barrel at a blinding speed, carrying a massive amount of forward momentum. To preserve the universe's perfect balance of zero total momentum, the massive steel cannon must instantly react. It undergoes a violent recoil, leaping backward in the opposite direction at the exact same moment the ball flies forward. Because the cannon has vastly more mass than the ball, its backward velocity is much slower, but its backward momentum is perfectly identical in strength to the ball's forward momentum. The forward and backward values, pointing in opposite directions, cancel each other out perfectly, ensuring that the total momentum of the system remains exactly at zero, just as it was before the fuse was lit. Let us set these profound images down now, letting the click of the billiard balls and the roar of the cannon dissolve into a deep, serene silence within your mind. We have seen how mass and velocity weave together to create a momentum that the universe guards with absolute jealousy, transferring it with flawless precision, but never allowing a single drop to be destroyed. And with that understanding quietly in place, we are naturally led to ask what happens when forces don't just push in straight lines or transfer back and forth in sudden crashes, but instead pull objects into beautiful, recurring curves and eternal loops. That is what we will gently explore next. Circular motion and centripetal forces. A moment ago, we ended with the idea of straight-line paths, collisions, and the beautiful conservation of momentum across an isolated system. Let us now turn our minds away from linear paths and step into a world governed by the elegant, recurring geometry of the circle. Up until this point in our journey, when we visualized an object changing its velocity, we naturally imagined it speeding up or slowing down along a straight track. But some of the most mesmerizing movements in our physical reality do not travel in straight lines at all. Instead, they turn, loop, spin, and orbit, tracing continuous curves through space. To explore how the laws of motion adapt to this curved landscape, let us imagine a wide, open meadow at dusk. The sun has dipped completely below the horizon, leaving the sky painted in deep shades of violet and indigo. The air is warm, heavy, and perfectly still. Imagine you are standing in the center of this open grass, holding the smooth leather handle of a long, sturdy rope. Attached to the far end of this rope, several feet away, is a small, heavy stone made of polished granite. Slowly, with a graceful and patient rhythm, you begin to swing your arm, lifting the stone off the ground and spinning it in the air directly above your head. As your hand guides the motion, The rope tautens, and the stone begins to whirl rapidly through the dark, tracing a flawless, horizontal circle against the twilight sky. Close your eyes in your mind and listen to the rhythmic, hypnotic whoosh of the stone slicing through the air, looping around and around you with a steady, unvarying beat. As you stand there spinning the rope, let us analyze exactly what is happening through the rigorous lens of Newton's laws of motion. If you look at the stone's speedometer, you might find that it is traveling at an absolutely constant speed, perhaps 20 miles per hour. But remember our earlier definition of acceleration from classical mechanics. Acceleration is a change in velocity over time, and velocity consists of both speed and direction. As the stone travels along its circular loop, its direction of travel is altering at every single fraction of a microsecond. At one instant, it is heading north. A millisecond later, it is heading northwest, then west, then southwest. Because its direction is undergoing continuous, unrelenting modification, the stone is actively undergoing continuous, constant acceleration. Now, think back to the uncompromising rule of Newton's first law of motion, the law of inertia. Matter is fundamentally conservative. It possesses a deep, unyielding desire to simply keep doing exactly what it was doing a moment ago. Left entirely to itself, the stone's inertia does not want it to travel along a curved path. At any given moment, the stone's mass desperately desires to break free and fly away in a perfectly straight line that shoots off tangentially, touching only the outer edge of the circle. The only reason the stone does not escape into the darkness is because your hand is actively intervening. Your hand is continuously pulling on the leather handle, and that pull travels down the fibers of the rope, exerting a continuous, unyielding inward force that forcefully yanks the stone away from its straight-line ambitions, dragging it inward toward your hand. This center-seeking force is what physicists call centripetal force. It is critical to realize, at a rigorous college level, that centripetal force is not a new, exotic type of energy, nor is it a mysterious force that springs out of nowhere whenever something starts to spin. Rather, centripetal is simply a descriptive title, a label that means center-seeking. It refers to any net force that happens to point directly inward toward the center of a curved path, bending an object's trajectory into a loop. Depending on the scenario, the role of centripetal force can be played by many different physical actors. In the case of our stone in the meadow, the centripetal force is provided entirely by the physical, mechanical tension of the rope pulling inward. To feel the reality of this force, let us imagine that as you are spinning the stone, you suddenly release your grip on the handle, or the sturdy fibers of the rope snap cleanly in two. What happens to the stone in that exact, breathless microsecond? A common misconception, one that confuses casual observers, is the belief that the stone will fly directly outward, away from your hand, as if expelled by a mysterious centrifugal force pushing it from the inside. But Newton's first law tells us the true story. The instant the rope snaps, the inward centripetal force vanishes entirely. The net force on the stone drops to zero. With the geometric bond broken, the stone instantly obeys its own natural inertia. It does not fly outward. Instead, it shoots off along a perfectly straight line, flying off at a right angle to the rope, traveling at that exact same speed of 20 miles per hour, until the gravity of the earth finally pulls it down into the grass far away. We see this elegant, center-seeking principle sculpting the mechanics of our everyday lives, hiding in experiences we take completely for granted. Think of a time when you have traveled inside a car that takes a sharp, fast turn around a curved highway exit ramp. As the car swerves hard to the left, what does your body feel? You feel yourself thrown forcefully to the right, your shoulder pressing firmly against the passenger door. Once again, it feels as though a phantom force is pushing you outward, away from the turn. But in reality, there is no outward force acting upon you at all. Your body, carrying its own massive inertia, simply wanted to keep traveling straight forward in the direction it was heading before the exit ramp began. As the car tires grip the asphalt and push the vehicle to the left, the passenger door literally swerves into your shoulder, scooping you up and forcing your stubborn mass to bend its path along with the chassis. The door applies the inward, centripetal force to your body, conquering your linear inertia and dragging you into the turn. Think of a modern washing machine during the spin cycle. The wet clothes are placed inside a heavy metal drum perforated with thousands of tiny holes. When the machine begins to spin at high speed, the solid metal walls of the drum continuously push inward against the clothes, providing the centripetal force that forces the fabric to travel in a rapid, blurring circle. But what happens to the water droplets clinging to the threads of the shirts and socks? When a droplet reaches one of the tiny holes in the drum, the solid metal wall is no longer there to push against it. The inward centripetal force on that specific droplet instantly vanishes. Obedient to its own inertia, the water droplet flies straight out through the hole in a tangential line, escaping the circle entirely, while the clothes are held fast within the machine, leaving them damp but thoroughly drained of excess water. Let us set these spinning, looping images down now, letting the whirl of the stone and the roar of the car tires dissolve into a deep, comforting stillness within your mind. We have seen how circular motion is not a state of passive rest, but a state of continuous, dynamic acceleration managed by an inward, center-seeking force that continuously fights against the stubborn, straight-line desires of inertia. We understand that to bend a path is to wage a constant, geometric war against the conservative nature of matter. And with that understanding quietly in place, we are naturally led to lift our eyes away from the ropes we can hold in our hands and the exit ramps we can drive upon, and look up toward the grand, silent cosmic theater. How does this center-seeking force operate when there are no physical ropes or metal walls to guide the path, spanning the vast, empty gulfs of space to hold entire worlds in check? That is what we will gently explore next. The gravity of the situation. Universal gravitation. Introduced. Before we rest here, let us extend our vision far beyond the things we can physically touch. Step outside the boundaries of our immediate surroundings and enter the grand, silent, cosmic theater. Up until this point in our journey, all the interactions we have examined have been tangible and immediate. We looked at hands pushing wooden crates, skates pressing against frozen ponds, ropes pulling on spinning stones, and car tires gripping the rough asphalt of an exit ramp. These are forces born of direct contact, mechanics that we can easily feel with our nerve endings and see with our eyes. But as humanity began to map the deeper rhythms of the world, a hauntingly beautiful question began to echo through the centuries. What holds the entire cosmos together when there are no hands, no ropes, and no solid walls to guide the paths of the stars? For a very long time, the rules of mechanics that we have just discussed were thought to apply strictly to our earthly home, a small, localized quirk of our imperfect planet. People believed that the sky operated on a completely separate, mystical paradigm. But one quiet afternoon in the 17th century, a profound, world-shattering realization struck the mind of a young Isaac Newton while he was taking refuge in a tranquil orchard. The story has been told for generations, passed down like a sacred myth. But let us look past the simplistic fable and feel the true, raw, intellectual wonder of that moment. Picture yourself sitting quietly beneath the low, twisted branches of an ancient apple tree on a warm, breathless autumn afternoon. The air is perfectly still, carrying the sweet, crisp scent of ripening fruit. You are leaning your back against the rough bark of the trunk, looking out over a rolling landscape that stretches toward the distant horizon. Suddenly, breaking the absolute silence of the afternoon, a single, heavy red apple detaches from its twig high above. It does not lift upward into the sky, nor does it drift sideways on the breeze. It falls straight down, plunging through the air in an unwavering vertical line until it strikes the soft green grass with a gentle thud, coming to an immediate rest right beside your hand. At that exact, fleeting moment, you look up through the gaps in the green leaves and notice something else hanging in the pale blue daytime sky. The faint, white crescent of the moon, riding high above the clouds like a ghostly ship. A normal person looks at the falling apple and looks at the distant moon and sees two entirely separate events that have absolutely nothing to do with each other. The apple is a mundane piece of fruit falling to the dirt, while the moon is a pristine celestial body traveling along its eternal, circular path through the heavens. But in that breathtaking flash of insight, Newton's mind built a magnificent, invisible bridge across the sky. He asked himself a radical, almost heretical question. Could the very same invisible hand that pulled the apple down to the earth be the exact same hand that holds the moon in its orbit? What if the force pulling the fruit to the dirt does not stop at the tops of the trees? What if it extends up past the mountains, up through the clouds, past the atmosphere, stretching out across thousands of miles of empty space until it reaches the silver face of the moon itself? This was the monumental birth of the law of universal gravitation, a concept that completely erased the ancient boundary between heaven and earth. It was the realization that gravity is not a localized terrestrial accident, but a universal bond that exists between every single piece of matter in existence, regardless of its size or location. Matter calls out to matter across the empty void of space, binding the entire cosmos together in a silent, delicate web of mutual attraction. It is an intrinsic property of mass to pull on other mass, a quiet gravity that requires no physical contact, no intermediate ropes, and no atmosphere to carry its message. It operates flawlessly through the cold vacuum of space, ensuring that no object is ever truly alone or completely disconnected from the rest of the universe. To understand this at a rigorous, college-ready level, we must realize that gravity is an attractive force that exists between any two objects that possess mass. Every single atom in your body exerts a tiny, invisible, but real gravitational pull on the person sitting next to you, on the walls of the room around you, and on every star burning in the most distant, unmapped galaxies at the edge of the cosmic horizon. And those people, those walls, and those distant stars are actively pulling back on you with the exact same amount of force in return. You might wonder why, if this pull is truly universal, you don't feel yourself physically flying across the room to stick to your refrigerator or your desk. The answer lies in the sheer, staggering weakness of gravity as a fundamental force. Compared to the forces that hold atoms together or power electrical currents, gravity is a gentle whisper. It is so faint that you only notice its presence when at least one of the participating masses is absolutely astronomical in size. You do not feel the gravitational pull of your desk because its mass is tiny, yielding an attraction that is far too weak to overcome the friction of your shoes on the floor. But the earth beneath your feet is a colossal sphere made of sextillions of tons of rock, iron, and water. Its mass is so grand that its collective whisper becomes a booming command, anchoring you firmly to its surface, pulling on your limbs with a heavy, continuous intensity that we experience every second as our weight. When Newton applied this radical concept to the moon, he realized that the moon is participating in the exact same circular dance we explored in our previous section. Think back to the stone whirling on the end of the rope in the dark meadow. The stone only stayed in its circle because the physical tension of the rope was continuously pulling it inward toward your hand, acting as a centripetal force. Without that rope, the stone's inertia would make it fly off in a straight line. The moon, carrying its own immense mass, possesses an incredible amount of forward linear inertia. Left entirely to itself, it wants to shoot off into the dark void of space, traveling along a straight path that would carry it away from the Earth forever. The only reason it doesn't escape is because the Earth is continuously pulling on it. There is no giant steel cable connecting our planet to the moon, no physical rope binding them together. Instead, the invisible gravity of the Earth reaches across the vast 300,000-kilometer gulf of empty space, continuously tugging on the moon's mass, acting as a perfect cosmic centripetal force that bends its straight-line path into a beautiful, eternal circle. The moon is held captive by an invisible gravitational string, tracing its path around us in perfect obedience to the same laws that govern a stone spun by a child. Let us let this profound image settle gently within your thoughts. Imagine looking out at the solar system from a high vantage point, stripping away the illusion of empty space, and instead seeing the planets, moons, and stars held fast by these invisible, glowing threads of gravitational attraction. The universe is a single, interconnected family, where the smallest pebble on a beach is bound by the exact same rules of attraction as the grandest galaxy swirling in the dark. And with that understanding quietly in place, we are naturally led to ask, how exactly does the universe decide how strong this invisible bond should be? What rules govern the intensity of this cosmic pull? And how does the distance between two worlds alter the strength of their silent conversation? That is what we will gently explore next. The mathematics of attraction, the inverse square law defined. A moment ago, we introduced the universal pull of gravity, bridging the ancient gap between heaven and earth by realizing that the same invisible hand that pulls a ripe autumn apple to the orchard grass also holds the moon in its eternal, circular embrace. Now, let us step deeper into the beautiful architecture of this cosmic bond and examine exactly how the universe decides how strong this pull should be. To do this, we must transition from a general, poetic understanding of attraction into a precise, rigorous, and college-level analysis of its mathematical relationships. Do not let the word mathematical cause you any hesitation or tension. We are not going to scratch a single symbol, equation, or variable onto a page. Instead, we are going to describe these elegant mathematical laws entirely in plain, spoken English, building a deep, intuitive monument of understanding within your mind. Newton's law of universal gravitation dictates that the gravitational force between any two objects in the cosmos is determined by two primary factors: the total mass of the objects themselves and the precise distance separating their centers. When expressed conceptually, the law states that the gravitational force is directly proportional to the product of the two interacting masses and inversely proportional to the square of the distance between them. To truly digest this, let us break this grand statement into two distinct, manageable halves, exploring each relationship through the calm, clear theater of our imagination. Let us begin with the first half of the rule, the direct proportion to the product of the masses. Imagine a quiet, empty expanse of deep space, far away from the distracting gravitational fields of any planet or star. In the center of this dark void float two small spheres made of pure, refined lead. They are sitting near each other, completely still. Because they possess mass, they feel a very faint, subtle, gravitational attraction toward one another. If left entirely alone over the course of many days, they would slowly, inevitably drift together until their surfaces touched. Suppose you were to reach out your hand in this imaginary void and, with a wave of a magic wand, instantly double the mass of the first lead sphere, packing twice as many lead atoms into its form while keeping its size the same. Because gravity is directly proportional to mass, the invisible pull between the two spheres instantly doubles in strength. The larger mass calls out with twice the intensity. Now, let us imagine that you wave your wand a second time, and you double the mass of the second sphere as well. Now, both spheres are twice as heavy as they were when you started, because the relationship depends on the product of the two masses, meaning you must multiply the two changes together. 2 times 2 equals 4. The gravitational attraction between the two spheres has now become exactly 4 times as strong as it was in the beginning. If you were to multiply the mass of one sphere by 10, the force would grow tenfold. If you were to multiply the mass of both spheres by 10, 10 times 10 equals 100, and the gravitational bond between them would explode to 100 times its original strength. This is why you and I can stand next to each other and never feel our bodies physically pulled together. Our individual masses are simply too small for their product to yield an attraction that can overcome the friction of our surroundings. But when you stand on the surface of the Earth, you are multiplying your modest mass by the staggering, colossal mass of an entire planet. The resulting product is immense, creating a heavy, unyielding downward pull that anchors you firmly to the ground. Now, let us turn our attention to the second, far more fascinating and geometrically beautiful half of the relationship, the inverse square law of distance. This is the principle that dictates how gravity fades as objects drift apart, and it is one of the most foundational concepts in all of classical physics. The law states that the force of gravity is inversely proportional to the square of the distance between the centers of the two objects. To feel the magic of this geometry, let us return to our two lead spheres floating in the deep void of space. Let us imagine that they are placed a specific, comfortable distance apart, say, exactly 1 meter from center to center. At this distance, they experience a certain baseline level of gravitational pull. Now, imagine you reach out your hands, capture the spheres, and physically pull them away from each other until they are now exactly 2 meters apart. You have doubled the distance between them. A casual observer might guess that because the distance has doubled, the gravitational force should simply be cut in half. But the universe does not operate on simple linear paths. It operates on the elegant rules of geometry. Because the force is inversely proportional to the square of the distance, you must take the factor of change, which is 2, and multiply it by itself. 2 squared equals 4. And because the relationship is inverse, meaning it behaves like a fraction, the gravitational force does not drop by half. It plummets to exactly 1/4 of its original strength. Let us carry this thought experiment a step further to let the concept truly crystallize. Suppose you pull the 2 lead spheres even farther apart, placing them at a distance of exactly 3 meters, 3 times their original separation. To find out what happens to the gravitational bond, we take that factor of 3 and square it. 3 times 3 equals 9. Because it is an inverse relationship, the gravitational force drops to a mere 1/9 of its baseline value. If you move them 4 meters apart, 4 squared is 16, meaning the force thins out to just 1/16 of what it was when they were close. If you separate them by a factor of 10, 10 squared is 100, and the gravitational attraction between them collapses to a tiny, fragile 1/100th of its original intensity. To understand why the universe behaves this way at a rigorous, college-ready level, we must visualize gravity not as a single physical rope pulling between 2 points, but as an invisible field of influence that radiates outward from a mass in all directions, forming a perfect, expanding sphere. Imagine a glowing candle burning in the center of a pitch-black room. As the light leaves the candle's wick, it travels outward in every direction simultaneously. As that light moves farther and farther away from the center, the same initial amount of light energy must stretch out to cover a larger and larger surface area. The surface area of a sphere is directly related to the square of its radius. Therefore, when the light has traveled twice as far, it must spread itself out over an area that is 4 times larger, making the light appear 4 times dimmer at any single point. When it has traveled 3 times as far, the area grows 9 times larger, and the light becomes 9 times fainter. Gravity behaves exactly like that candlelight. The gravitational influence of a mass spreads out evenly across the geometry of expanding spheres. As the distance grows, the strength of the field thins out with extreme mathematical rapidity, diluting its power across the vast canvas of space, stretching outward toward infinity, but never truly reaching absolute zero. No matter how many millions of miles you travel away from the Earth, our planet's gravity never completely vanishes. It merely thins out until it becomes a silent, imperceptible whisper, a tiny fraction of a percent, still holding a ghost of a connection to your mass. Let us set these geometric visions down now, letting the lead spheres and the expanding spheres of light dissolve into a calm, reassuring stillness within your mind. We have seen how the universe balances the ledger of attraction, combining the product of masses with the rigorous geometry of the inverse square law to determine the exact strength of the invisible bonds that tie the cosmos together. We see that the universe is governed by a beautiful, mathematical harmony that ensures everything is weighted, measured, and perfectly accounted for. And with that understanding quietly in place, we are naturally led to ask, how does this thinned-out gravitational pull manifest when objects find themselves falling right here beneath our feet, near the heavy surface of our own planet? How does this mathematical attraction translate into a constant, predictable acceleration for all things? That is what we will gently explore next. Acceleration, due to gravity, and the Galileo experiment. Let us bring our minds back down from the deep, dark gulfs of interstellar space, returning our focus to the surface of our beautiful, blue planet Earth. We have explored the grand geometry of the inverse square law and watched how the invisible field of gravity dilutes its strength as it spreads across the expanding spheres of space. But when we stand right here on the ground, the distance between our feet and the center of the giant planet beneath us is essentially fixed. Because this distance is constant, the planet's gravitational pull manifests as a steady, predictable phenomenon that every single piece of matter must obey. This brings us to a classic, elegant mystery that puzzled the greatest minds of humanity for thousands of years, a riddle that was finally unlocked by a combination of Newtonian insight and one of the most famous experiments in the history of science. For generation after generation, the common sense wisdom of humanity dictated that heavier objects must naturally fall through the air much faster than lighter ones. It seemed completely undeniable, an obvious truth written into the very fabric of daily life. If you were to walk out into a garden, pick up a heavy, solid stone ball, and at the exact same moment, release a delicate, fluffy bird feather from your hand, your eyes would tell you a very clear story. The heavy stone ball crashes down through the air in a violent fraction of a second, hitting the soil with a thud. Meanwhile, the feather drifts lazily on the afternoon breeze, floating, twisting, and taking a long, leisurely path before finally resting on the grass. Based on this everyday observation, the ancient philosopher Aristotle concluded that the speed at which an object falls is directly determined by its weight. For nearly 2,000 years, no one challenged this rule, because no one learned to look past the hidden distortions of our environment. But let us imagine a magnificent historical turning point, an experiment traditionally attributed to the brilliant scientist Galileo Galilei at the Leaning Tower of Pisa, and later fully explained by the rigorous laws of Newtonian mechanics. To see the true truth of this phenomenon, we must use the power of our imagination to build a perfect laboratory, stripping away the messy, chaotic air that surrounds our planet. Picture yourself standing at the absolute peak of a magnificent, towering stone monument. The air is completely still, and through a miracle of modern thought, we are going to press a cosmic button that instantly drains all the atmosphere out of the area around the tower, leaving behind a pristine, warm, and perfect vacuum. In this quiet sanctuary of pure physics, there is not even a single molecule of gas left to brush against a moving object. There is no wind, no air resistance, and no atmospheric friction. There is only the pure, undisturbed pull of the Earth's gravity acting on the space below. Imagine standing on the edge of this high tower, looking out over a silent, breathless landscape. In your left hand, you are holding a massive, heavy iron cannonball that weighs a full 50 pounds. In your right hand, you are holding a tiny, delicate, glass marble that weighs less than a single ounce. Feel the contrast in your hands. The cannonball is dense, heavy, and strains your muscles. The marble is light, fragile, and sits effortlessly on your palm. Now, take a deep, slow breath. Bring your hands perfectly level over the edge of the tower and release them both at the exact same cosmic microsecond. Without the grasping hands of air resistance to interfere, a breathtaking, beautiful truth reveals itself to your mind. The massive iron cannonball and the tiny glass marble do not separate. They fall through the dark vacuum completely, side by side, dropping at the exact same rate, traversing the exact same distance with every passing millisecond, as if they were locked together by an invisible rod. They race down the side of the tower in perfect harmony, and with a single, synchronized impact, they strike the ground at the exact same instant. The 50-pound iron ball and the 1-ounce glass marble arrived at the finish line together, completely destroying the ancient idea that weight dictates the speed of a fall. To understand why the universe behaves in this deeply counterintuitive way at a rigorous, college-ready level, we must bring together two different laws that we have already explored in our journey: Newton's second law of motion and the law of universal gravitation. Think about the ledger of forces acting on these two falling objects. According to the law of gravitation, the Earth pulls on an object based on its mass. Because the iron cannonball possesses vastly more mass than the tiny glass marble, the Earth pulls down on it with a massive, terrifyingly large amount of gravitational force. The cannonball is being yanked toward the ground with 50 pounds of active downward pull. The marble, on the other hand, experiences only a tiny fraction of an ounce of downward pull. You might think that because the cannonball experiences a force that is hundreds of times stronger, it should accelerate hundreds of times faster. But now, remember Newton's second law of motion, which states that acceleration is equal to the net force divided by the mass. The cannonball does experience a massive downward force, but because it is so heavy, it also possesses a massive amount of quantified inertia. It has an immense, stubborn, internal resistance to changing its motion. It requires a huge amount of force just to get its heavy frame to move at all. When you look at the mathematical relationship in plain English, the universe has set up a perfect, elegant balance. The extra gravitational force experienced by the heavy cannonball is completely and precisely used up, conquering its extra internal inertia. The greater pull is perfectly canceled out by the greater resistance. For the tiny marble, the tiny downward force is perfectly sufficient to conquer its tiny internal inertia. When you divide the force by the mass for each object, the mass cancels out of the equation entirely. The universe wipes the slate clean, leaving both the giant cannonball and the tiny marble to experience the exact same rate of change. Near the surface of our Earth, this flawless, symmetrical cancellation results in a single, constant numerical value that all falling bodies must experience. The acceleration due to gravity, often labeled simply as g, in the clear language of science, this acceleration is roughly equal to 9.8 meters per second, every single second. To feel what this means, let us visualize a skydiver dropping from a stationary helicopter into our perfect vacuum. The moment they let go of the fuselage, their speed is 0. After 1 full second has ticked by on your stopwatch, gravity has accelerated their mass, and they are plunging downward at a speed of 9.8 meters per second. After a second passes, gravity adds another 9.8 meters per second to their journey, bringing their speed to 19.6 meters per second. After 3 seconds, they are traveling at 29.4 meters per second. Every single second that an object falls through a vacuum, its downward velocity increases by that exact same steady, relentless increment, regardless of whether that object is a tiny grain of sand, a heavy cannonball, a grand piano, or a mountain. Gravity is a completely democratic force, accelerating every single atom in existence at the exact same rate, treating all matter with a beautiful geometric equality. Let us set these falling images down now, letting the cannonball and the marble rest safely on the ground within your thoughts. We have seen how the universe eliminates the factor of mass from the story of a falling body, matching a greater pull with a greater resistance to create a constant, unwavering acceleration that governs the descent of all things. We understand that the apparent differences we see in our daily life, the slow drift of a feather, are not the fault of gravity, but are merely the chaotic interference of the atmosphere we breathe. And with that understanding quietly in place, we are naturally led to lift our eyes from the objects falling to the ground and look up toward the horizon. What happens if an object is falling toward the earth, but it is also traveling sideways with an incredible, explosive speed? How can this constant downward drop be transformed into an eternal, looping journey that never touches the earth? That is what we will gently explore next. Orbital mechanics, falling forever into space. Let us pick up the thread of falling objects and elevate it to a grand, cosmic scale, transitioning from the vertical drops of a tower into the beautiful, perpetual loops of orbital mechanics. We have established that near the surface of the Earth, every single object falls with the exact same relentless acceleration of 9.8 meters per second squared, provided we strip away the chaotic interference of air resistance. Now, let us take this concept of a constant, predictable drop and merge it with the forward linear inertia we explored in our circular motion journey. To see how these two principles weave together to conquer the heavens, we must build a magnificent, daring thought experiment in the quiet laboratory of our imagination, a concept first visualized by Newton himself, often called Newton's orbital cannon. Imagine traveling to the absolute peak of an impossibly tall, majestic mountain. This mountain is so colossal that its summit rises completely out of the Earth's atmosphere, piercing through the heavy layers of blue air and reaching high into the absolute stillness of deep space. Up here, at the peak, there is no weather, no wind, and no friction. The sky above and around you is an intense, velvety black, dusted with millions of diamond-like stars that never twinkle. Looking down, you can see the grand, curved horizon of the round Earth stretching away beneath you like a massive blue and green marble. On the very summit of this mountain, you have placed a massive, powerful cannon, aligned perfectly horizontal, pointing straight out parallel to the curved ground far below. Let us load this cannon with a standard iron cannonball and pack a modest, conservative amount of gunpowder into the breech. Take a slow, deep breath, feel the absolute silence of the vacuum, and fire the weapon. With a silent flash of light, the cannonball blasts out of the barrel, traveling horizontally at a decent speed. What path does it take? The moment it leaves the muzzle, its forward linear inertia wants it to fly off in a perfectly straight line, shooting out into the dark void of space. But at that exact same microsecond, the massive gravitational pull of the Earth reaches up and grabs the cannonball, accelerating it downward at 9.8 meters per second squared. As a result of these two competing desires, the forward glide of inertia and the downward plunge of gravity, the cannonball traces a gentle, downward curving arc through space, eventually slamming into the Earth's surface a few miles away from the base of the mountain. Now, let us step back to the cannon and increase the stakes. You load a second iron ball, but this time, you pack twice as much gunpowder into the chamber. You light the fuse, and the ball explodes out of the barrel at twice the horizontal speed of the first shot. Because its forward velocity is much grander, its linear inertia carries it much farther forward in the first few seconds of its flight. Yet, gravity is entirely democratic. It still pulls the ball downward at that exact same steady acceleration. Because the ball is traveling forward so quickly while it drops, it traces a much wider, flatter, and more elongated curve through space, soaring over hills, valleys, and oceans before it finally succumbs to the Earth's pull and crashes into the ground hundreds of miles away. Now, let us prepare for the ultimate, breathtaking synthesis of classical physics. You load the cannon one final time, and you pack it with an explosive, precisely calculated, and astronomical amount of gunpowder. You fire the weapon, and the cannonball screams out of the muzzle at a blinding, staggering speed, roughly 17,500 miles per hour. Watch the journey of this ball with absolute wonder in your mind. The cannonball flies forward with such incredible velocity that a miracle of planetary geometry unfolds. As the powerful gravity of the Earth pulls the cannonball downward, causing its path to curve toward the ground, the round Earth itself begins to curve away beneath it at the exact same mathematical rate. For every mile the cannonball drops vertically toward the surface, the planet's spherical horizon curves downward by that exact same depth. Picture this breathtaking balance in your mind. The cannonball is actively falling toward the ground, plunging through space under the continuous acceleration of gravity, but the ground is curving away beneath it, retreating at the exact same pace. The cannonball keeps falling, but it can never, ever reach the surface. It chases the horizon forever, tracing a beautiful, unbroken, and perfect circle completely around the globe, passing right back over the peak of the mountain where it started, and continuing onward into its second, third, and millionth lap. The cannonball has entered a state of permanent, eternal orbit. To understand this concept at a rigorous, college-ready level, we must dispel a massive, almost universal misconception that plagues the popular imagination. When people watch videos of astronauts floating gracefully inside the International Space Station, flipping through the air and letting their food hover in front of them, they assume that this weightlessness is because the spacecraft has traveled so far away from the Earth that it has escaped the planet's gravity entirely. They believe space is a realm of zero gravity, but this is a complete scientific illusion. The International Space Station orbits only a few hundred miles above our heads. At that altitude, the Earth's massive gravitational pull is still incredibly strong, retaining roughly 90% of the intensity that we feel standing right here on the ground. The astronauts are not weightless because there is no gravity. They are weightless because they are in a state of continuous, unending freefall. To feel the intuitive truth of this, imagine stepping into an elevator at the top of a glittering skyscraper. Suppose that the moment the elevator doors close, the steel cables snapping cleanly in two, sending the elevator car plunging into a terrifying, unhindered freefall down the shaft. If you were to release your grip on your car keys inside that falling elevator, the keys would not drop to your feet. Why? Because the keys are falling toward the Earth at 9.8 meters per second squared. But the floor of the elevator is also falling toward the Earth at that exact same rate. The keys would hover perfectly in midair right in front of your face. If you were to give yourself a gentle push off the floor, you would float upward to the ceiling, experiencing absolute, pure weightlessness inside the car. Gravity is still pulling you down with immense force, but because your entire environment is dropping along with you, you lose all physical sensation of weight. This is exactly what is happening to an astronaut or a satellite orbiting the Earth. The International Space Station is nothing more than that falling elevator car, but instead of dropping straight down a vertical shaft to a catastrophic crash, it is traveling sideways at 17,500 miles per hour. It is falling around the Earth, continuously dropping toward the horizon, while its forward speed ensures that it keeps missing the planet entirely. The astronauts float inside their metallic home because they, their toothbrush, their computers, and the spacecraft itself are all falling together in a continuous cosmic drop that never meets an ending. They are cradled by gravity, held fast by an invisible gravitational string that bends their linear inertia into a perpetual circle of balance. Let us set these grand, sweeping orbital visions down now, letting the cannonball and the space station glide smoothly into the quiet background of your thoughts. We have seen how the simple acceleration of a falling body, when married to an explosive horizontal speed, breaks the bonds of the Earth and transforms a violent drop into an eternal journey of celestial grace. We understand that an orbit is not the absence of gravity, but the ultimate expression of gravity, working in perfect geometric harmony with inertia to dance across the stars. And with that understanding quietly in place, we are naturally led to ask how these incredible insights transformed our view of the entire universe. If the same rules apply to apples, cannonballs, and the moon, what does this say about the predictability of existence? How does this mechanical harmony shape our philosophical understanding of time, destiny, and the grand clockwork of reality? That is what we will gently explore next. The clockwork universe and determinism. So what does this actually mean for how we view reality itself? As the profound realizations of Newton's laws of motion and universal gravitation spread across the civilized world, they did not simply change the way humans designed machines or navigated ships. They did something far more sweeping and permanent. They fundamentally altered the psychological, philosophical, and spiritual landscape of human consciousness. For millennia, existence had been viewed as a deeply mysterious, often terrifying landscape governed by caprice, whim, and unpredictable forces. The ancient world looked at a sudden solar eclipse, a violent thunderstorm, or the erratic path of a comet as a sign of divine anger or chaotic instability. But as the elegant geometry of classical mechanics took root, the universe suddenly shed its frightening mask of randomness, revealing instead an immense, beautifully ordered, and completely predictable masterpiece of design. This profound philosophical perspective became known across Europe and the world as the concept of the clockwork universe. To truly feel the depth of this worldview, let us build a vivid image of it in our minds. Imagine walking into the quiet wood-paneled study of a master artisan. In the corner of the room stands a magnificent, towering grandfather clock crafted from dark, polished mahogany. Step closer and listen to its steady, rhythmic, and deeply comforting heartbeat. Tick, tock, tick, tock. Now, imagine opening the glass casing on the side of the clock to look directly at the intricate machinery inside. The interior is a breathtaking labyrinth of polished brass cogs, steel gears, winding springs, and counterweights. Every single tooth of every single gear is perfectly notched into the tooth of the gear next to it. When the mainspring unwinds, it exerts a precise, unvarying force that turns the primary wheel. That wheel turns a secondary cog, which swings the heavy pendulum back and forth with flawless, mathematical regularity, translating the raw tension of gravity into the graceful, steady sweeping of the hands across the clock face. There is no randomness here. There is no hesitation, no uncertainty, and no room for deviation. Every single movement of every single microscopic atom of brass inside that clock follows with absolute, inescapable necessity from the physical rules of its construction. If you know the shape of the gears and the tension of the spring, you can predict, with 100% certainty, exactly where the hands of the clock will point an hour from now, a year from now, or a century into the future. In the wake of the Newtonian revolution, the greatest thinkers of the Enlightenment looked up at the stars, looked down at the tides, and realized that the entire cosmos is nothing more than this grand grandfather clock, scaled up to an astronomical dimension. The sun, the earth, The moon, the distant planets, and the swirling nebulas are all cogs and gears locked into a single, flawless, and universal mechanical embrace. The law of gravitation is the invisible spring that drives the motion, and the three laws of motion are the unchanging rules that govern how the teeth of the gears interact. The same mathematical ledger that predicts the slow, steady swing of a clock's pendulum describes the trajectory of a comet returning from the freezing outer edges of the solar system, or the falling of a stone to the ground. This realization gave birth to the philosophy of strict physical determinism, a concept most beautifully articulated by the brilliant French mathematician Pierre-Simon Laplace. Laplace took the laws of Newton to their absolute logical extreme, creating a famous thought experiment that challenges our very understanding of time and free will. Let us explore this idea calmly and deeply. Imagine an intellect so grand, so vast, and so astronomically powerful that it could know, at any one single instant, the exact position, the exact mass, and the exact velocity of every single subatomic particle in the entire universe, from the massive core of a burning star to the tiniest speck of dust floating in the air of your room. If this intellect, often called Laplace's demon, could take that unimaginable mountain of data and plug it into Newton's second law of motion, it could calculate the entire past and the entire future of the cosmos with absolute mathematical perfection. For such a being, nothing would be uncertain. The future would be present before its eyes, just like the past. The exact day a distant star will explode into a supernova, the exact pattern of ripples that will form when a raindrop hits a puddle 1,000 years from now, and even the exact thoughts crossing your mind at this very moment would be written into the initial settings of the cosmic machine, marching forward with the absolute, unyielding inevitability of a clock ticking toward midnight. To understand this at a rigorous college level, we must recognize the immense comfort and the profound existential weight this philosophy brought to human thought. On one hand, it offered an unparalleled sense of safety and order. It declared that nature was completely rational, knowable, and friendly to human reason. The universe was no longer a haunted house filled with ghosts and unpredictable monsters. It was a magnificent classroom where any patient student could learn to read the divine blueprint. It meant that humanity could use its mind to conquer the chaos of the world, forecasting the movements of the planets to navigate the seas, or calculating the stresses on iron beams to build bridges that could withstand the fury of a river. It suggested that beneath the apparent confusion of daily life, an eternal, mathematical harmony was always operating, ensuring that everything was weighted, measured, and perfectly accounted for in the universe's great ledger. On the other hand, this clockwork model posed a radical challenge to our deeply held beliefs about human freedom and agency. If the universe is a purely mechanical system where every single event is rigidly determined by the events that came before it, then are we truly the captains of our own souls? When you reach out your hand to pick up a glass of water, is that a spontaneous choice born of your own free will? Or is it merely the inevitable result of a long, unbroken chain of physical causes and effects, stretching all the way back to the dawn of creation? Classical mechanics pushed humanity into a strange, beautiful paradox. It made us masters of predicting the external world, but it threatened to turn our internal lives into the passive movements of puppets dancing to the tunes of mass and acceleration. Let us set these deep, philosophical reflections down now, letting the ticking of the grandfather clock and the vast calculations of Laplace's thought experiment fade into a quiet, gentle murmur within your mind. We have seen how the triumph of Newtonian physics transformed our understanding of reality, spinning a web of mathematical certainty across the vast canvas of time and space, leaving us with a universe that is profoundly orderly, beautifully predictable, and deeply unified under a single set of laws. And with that understanding quietly in place, we are naturally led to turn our eyes toward the final horizon of our educational journey. How do these grand classical principles, which describe our everyday world and the movements of the planets so flawlessly, fit into the broader story of modern science? How do they hold up when we push the boundaries of reality to the absolute extremes of space, time, and the subatomic realm? That is what we will gently explore next. The legacy of Newton and the horizon of modern physics. As we bring our thoughts back to the quiet room around you, let us appreciate the enduring legacy of the grand intellectual journey we have taken together. The laws of motion and universal gravitation, formulated by Sir Isaac Newton, stand as one of the most monumental achievements in the entire story of human consciousness. For nearly 3 centuries, this elegant, unified framework provided the absolute blueprint for the modern world. It was the torch that guided humanity out of the fog of ancient superstition and into the clear, brilliant light of the scientific age. Every time you cross a majestic suspension bridge that spans a wide river, every time you gaze up at a glittering skyscraper that pierces the clouds, and every time you watch a massive steamship navigate the ocean waves, you are witnessing Newton's mind actively at work in the physical world. It was this exact framework that allowed engineering to transform from a game of trial and error into a precise, flawless science. Because of the second law, we could calculate the exact thickness of steel required to support a locomotive. Because of the third law, we could understand how to shape the wings of an aircraft so that the air pushes it upward into the sky. When humanity finally gathered its courage to leap off its home planet and explore the dark void of space, it was not modern, exotic physics that charted the path. When the Apollo astronauts blasted off from Cape Canaveral, journeying through the cold 300,000-kilometer gulf of space to place their boots upon the gray dust of the moon, their trajectory was calculated using the exact same verbal equations we have explored tonight. The flight controllers did not need the mind-bending complexities of quantum mechanics or the grand distortions of relativity to reach the lunar surface. They simply needed the reliable, clockwork precision of Newtonian mechanics. Yet, as humanity entered the twilight of the 19th century, a subtle, beautiful shift began to occur in our relationship with nature. For generation after generation, scientists believed that Newton had written the final chapter of physics, that the universe was completely solved, and all that remained for future generations was to measure the constants out to a few more decimal places. But as we began to build finer instruments, peer deeper into the subatomic heart of matter, and look further into the cosmic vastness, the universe began to drop hints that its true nature was far stranger, far more fluid, and far more mysterious than the rigid, mechanical cogs of the classical clockwork model. To understand where classical physics meets its natural limit at a rigorous, college-ready level, let us imagine pushing the variables of reality to their absolute, breathtaking extremes. Newton's laws operate on a quiet, comfortable assumption that space is an absolute, unchanging stage, and that time flows at a steady, unvarying pace for everyone in the cosmos, completely independent of how fast an object is moving. For our everyday world, this assumption is so perfectly accurate that we never notice a single flaw. But imagine climbing into a conceptual starship that is capable of accelerating faster and faster until it is traveling at nearly the speed of light, roughly 186,000 miles per second. As your ship approaches this ultimate speed limit of the universe, the predictable world of Newton begins to warp and dissolve. This is the realm of Albert Einstein's special theory of relativity. Einstein realized that as an object approaches the speed of light, time itself begins to stretch and slow down compared to an observer who is standing still. Furthermore, the mass of the object does not remain constant, as it does in classical mechanics. Instead, the object's mass begins to swell toward infinity, requiring an infinite amount of force to cause even a tiny fraction of additional acceleration. In this extreme landscape, gravity is no longer seen as an invisible string pulling between two masses across flat space, as Newton imagined. Instead, through Einstein's general theory of relativity, we learn to visualize space and time woven together into a single, smooth fabric called space-time. A massive body, like our sun or the Earth, bends and warps this fabric, much like a heavy bowling ball resting on a flexible rubber sheet. When a planet orbits the sun, it is not being yanked by an attractive force. It is simply rolling along the natural, curved dips and valleys of a space-time fabric that has been bent by the sun's immense presence. Classical gravity is revealed to be a beautiful, highly accurate approximation of a deeper geometric reality. Simultaneously, when we turn our vision inward, diving deep into the microscopic realm to look at things that are smaller than a single cell, smaller than a strand of DNA, down to the level of individual atoms and electrons, the clockwork certainty of Newton encounters an even more radical boundary. This is the misty, fascinating world of quantum mechanics. In the classical world, everything is perfectly definite. A billiard ball has a precise position on the green felt, and it travels with a precise velocity that can be measured to the absolute decimal. But at the subatomic scale, nature refuses to be pinned down. An electron moving around an atomic nucleus does not travel along a clean, predictable, circular orbit like a miniature moon. Instead, it exists in a state of fuzzy, shimmering probability zones, acting sometimes like a solid particle and sometimes like a rippling wave. According to the famous uncertainty principle, the more precisely you try to measure where a subatomic particle is located, the less precisely you can ever know how fast it is traveling. The universe replaces the absolute determinism of Laplace's clockwork machine with a delicate game of cosmic dice, where probability and fluid possibility reign supreme. It is easy for a student of science to look at these modern revolutions and think that Newton was somehow proven wrong, that his laws were broken or discarded by the arrival of the 20th century. But this is a profound misunderstanding of how scientific truth grows and matures. Newton was not wrong. Rather, his laws represent a magnificent, flawless snapshot of reality across a specific, beautiful scale, the macroscopic realm where you and I live our lives. Classical mechanics is the true, authentic language of the human scale. It describes the world of things we can hold in our hands, the cars we drive, the buildings we inhabit, and the stones we drop from towers. It is an incredibly accurate, reliable, and elegant approximation that holds fast until you push the universe to the absolute edges of its parameters. When you look at a modern physics textbook, you find that if you take the mind-bending equations of relativity and plug in a normal, everyday speed, like the 30 miles per hour of a car or the 20 miles per hour of a spinning stone. The complex terms melt away, and the math collapses perfectly and beautifully back into Newton's second law. The modern universe does not destroy the classical world. It cradles it, recognizing it as the foundational stepping stone that allowed human reason to climb out of the dark. And so, as we let the vast horizons of relativity and quantum mechanics drift away into the quiet canvas of the night, we come to the absolute end of our time with Newtonian physics. Not an ending, really, but a beautiful, serene place to rest. You have let these profound ideas settle beside you as you listened, and they will remain here, woven into the fabric of your thoughts, whenever you return. You understand the quiet inertia that keeps things still, the active net forces that bring matter to life, the perfect mirrored symmetry of every action and reaction, and the invisible, universal gravity that connects the smallest pebble on a beach to the grandest galaxy, swirling in the dark void of space. You are a part of this grand, harmonious clockwork, completely safe within its predictable paths and mathematical beauty. Until then, breathe deeply, let go of every lingering worry, and sleep well, carrying nothing into your dreams but the quiet, comforting sense that you understand a little more of the magnificent universe than you did before.